exercise questions, set number 5. The first questions. So here I like to give you a few questions related to asymptotic notations. Yeah. All right, the first one is very easy. Yeah. Two positive functions f of n, g of n, said about this condition, limit ratio of these two, n goes to infinity, ratio equals 0. All right. Can we say that f of n belongs to little o of g of n? By the definition of little o, yes, right? That's the definition of little o. Yep. So, nothing more. Yeah. All right. So this is a simple one, very easy. But next one related to this one, could get you confused. Yeah. Could get you confused. So let's look at the next one. All right. So everything the same, but here I ask you if f of n is contained in the big O of g of n. So you can see the only difference with the previous one, we change little to big O. Is it correct? Is it correct? We know big O, upper bound, right? Upper bound. So there is a constant multiple, positive constant multiples of g of n that can be used as the upper bound for f of n when n is sufficiently large. That's the definition, right? Yeah. All right. Here the answer is yes. Why? Why? So let me convince you in this way. First, we know that limit is 0, right? F of n over g of n, that limit is 0, right? All right. So 0 less than 1, right? Positive constant less than 1. So then based on the limit definition, limit has a definition, right? So the limit definition based on the limit definition, right? So then when n is sufficiently large, so you can see, we always use this special wording. Yeah. We know that means n greater or equal to n some unspecified n0. If you like, we can find it. But most of the time, we don't need to find it. If someone really needs it, we can find it. But most of the time, we don't need it. All right. When n is sufficiently large, first we know these are two positive functions, right? F of n over g of n less than 1. That's the limit definition. So we have that, right? So positive functions, remember two positive functions. All right, yeah. Then we multiply g of n, the denominator, both sides. So we have f of n less than g of n. The constant c equals 1. Is this the big O condition? That's the big O condition. When n is sufficiently large, we have this inequality. Upper bound. This is upper bound, right? Upper bound. So we prove it. Okay? So it is correct. All right. Next question. The same condition, but the answer, the question, big theta. We change to big theta. The answer is no. The reason, very easy. We have the upper bound, but we don't have the lower bound. The reason is because big theta will require lower bound. Okay, yeah, will require lower bound. So here the reason is no lower bound. Okay, all right. You can use a counter example to see it, right? Yeah. For example, f of n equals n, g of n equals n squared. Okay, that condition is satisfied, right? N over n squared. When n goes to infinity, that's 0. But can you find the lower bound, or does it exist? Does there exist a constant c times g of n that is less than f of n, that c2 n squared less than n? You can never find a positive constant c. No such positive constant c2. There does not. Okay? Yeah. Can you see that? Why nobody can find such constant positive constant c2? It's very easy, because if someone can find it, c2 should be less than n over n squared, right? But this limit goes to 0. So when you make n goes to 0, the limit of right-hand side, 0, how can you get a positive number c2 less than 0, less than or equal to 0? You cannot get that. Contradiction. So this is a contradiction. Contradiction. All right, yeah. Contradiction. All right. Yeah, so that's the reason. Answer is no. Okay, answer is no. Yeah. All right. Then the last question of part 2, n factorial. So this one looks pretty complicated, right? Because there is n factorial. Remember, I told you before, when you see n factorial, you should bring up that Stirling's formula. So let's get that Stirling's formula. When you have this one, now you can take nth root. Take nth root. All right, so let's take everywhere nth root. Yeah. All right. So that part, nth root n over e less than nth root, okay, less than, the whole thing, e all right, yeah. Now let's take the limit. Limit. Also limit. Okay. All right, let's take it. Okay. When we take the limit, remember we should make this equal sign, add equal sign. Inequality, but when we take limit, we need to add equal sign. All right. So then when n goes to infinity, remember, this part goes to 1. That part also goes to 1. Can you see that? Yeah. All right. Can you see the limit 2 pi n root n goes to 1, because you can look at the two parts. The first part, 2 pi, this nth. Constant number, you take nth root, n goes to infinity, that is 1, right? Okay. The second part, root n nth Can you write n? So we just did this one equals 1 in our previous part, right? So root of 1 also 1. See? Yeah. So 1 times 1, that part of 1. This part also 1, similar to that, also 1. Okay. So you can see this, based on that, you can see approximately you can use n over e. When n is very large, 1 times n over e. Okay? N over e compared with n log n, which one is larger? Okay? Which one grows faster? So n log n grows faster. N over e, smaller than n, right? N log n, much bigger than n, because log n goes to infinity. So you can see b is larger. So when you use Stirling formula, okay, then you compare, all right, the main part, but you need to figure out the coefficient. Coefficient, you look at the limit. Look at the limit. The limit is 1. So you just think of 1 constant times that one. When n is very large, you can use n over e to approximate nth root of n factorial. All right, so that's part E.2.